Assalamualaikum and good afternoon. Today we will discuss a few questions from the tutorial. So we see tutorial number 6.8. Determine the shape factor h if the velocity profile is given as 2u over u equal eta by the power of 1 over 6. And it is given that eta is equal to y over delta. So here, in some textbook, they will use velocity profile in term of eta because Blasius use this symbol for the similarity problems. So it is okay for you. So the simple method to solve this one is just replace the value of eta with y over delta. Means you have u over u, capital U is now equal to y over delta over power of 1 over 6. So you could solve this problem by using this equation. But in this tutorial, I would like to show you what you should do if you want to solve problems here by remaining the value of eta in your equation. So first, the shape factor h is actually another dimensionless parameter that show us the possibility of certain flow to become laminar or turbulent. So the equation is delta star, which is the displacement thickness of boundary layer, divided by theta, which is the momentum thickness of boundary layer. So in this page, I show you how we convert equation from dy here to the eta here. So previously for delta star and theta, the equation to calculate displacement thickness and momentum thickness is given in this equation. So delta star is equal integration of 0 to delta 1 minus u over u dy, and theta is integration of u over u 1 minus u over u dy. So here we know that if you use u over u equal y over delta with power 1 over 6 here, you could replace this value into this term. Then you could get the value of delta star and also the theta. But if you want to use the symbol of eta, you need to change this equation. So the changes should become like this. So we assume that u over u is equal to function of eta. So and then we replace here 1 minus u over u here. So we replace into 1 minus f eta, function of eta. Then we need to change the dy here into d eta. So how to change this one? So we just use this idea. So let's say we have eta is equal y over delta. And then let's say we have a y is equal eta and delta here. So if we have dy here, so we will have delta over d eta. So we don't have the d delta because delta is the boundary layer thickness and the value of boundary layer thickness is fixed at certain value of x. So we replace the dy here with delta d eta, so we have this term. So again, I would like to remind you that you could solve boundary layer problems by using the y over delta or u over u, or you could change it into the terms of eta. So if you use the parameter of eta, you need to change the equation for delta star and also the theta. So this is the equation for the delta star, and now it's become 1 minus f eta times delta and d eta. And the limits here is also needs to be changed. So because from this equation, we could say that if y equal to 0, so the eta will be 0. And if y equal to delta, so we substitute delta here, so we get eta is equal to 1. So now the limit for the integration for this equation will become 0 to 1. And for Momentum thickness. So we have the integration 0 to 1 for f eta here. So it represents u over u, and 1 minus f eta and delta d eta to replace the value of dy. So please remember this one, because for velocity profile that has so many terms of y over delta, it is advantage for you to solve the that problem by using the idea of eta. So, and then we need to solve the value of h, and the value of h is delta star over theta. And then we know that our eta here, that our u over u, so is equal to eta by the power of 1 over 6. So we substitute, we use the delta star here. So we substitute the value of function of eta. And then we could get the delta star is equal 1 over 7 delta. We do the same things. So we calculate the value of theta here, and then we could get it is equal to 3 over 28 delta. And then to get delta star over theta, so it is equal of 1.333, which is 4 over 3 here. So what is the meaning of this dimensionless item is a shape factor is used in boundary layer flow to determine the nature of the flow. The higher the value of h, the stronger the adverse pressure gradient. A high adverse pressure gradient can greatly reduce the Renault number at which transition into turbulent may occur. Conventionally, h equal 2.59. The Blasius boundary layer is typical of laminar flows, but if your h is 1.3 to 1.4, it is typical of turbulent flows. So we go for question 6.14. Let's say we have a water at 20 degrees Celsius and 1 atm, flows at 6 meters per second, past a smooth flat plate with 1 meter long and 60 centimeter wide. And we take the Renault transition is 10 by the power of 6 here. So, and then we need to estimate the boundary layer thickness, the wall shear stress at the trailing edge. So trailing edge means at the end of this plate, and the drag force of one side of the plate. So as we explained in previous tutorial, if you have one plate like this, so the boundary layer may occur on the both sides. So the drag force that we calculated is actually represent the drag force only for one side. So we need to multiply with 2 to get the total drag force that affected the plate. So in this situation, we take the Renault transition, means the changes from laminar to turbulent is at 10 by the power of 6. So normally, if the transition value is not given in the question, you may use 5 times 10 by the power of 5, because this is the common assumption for the Renault transition. So let's say we take 10 by the power of 6 as our Renault transition here. So first, we calculate Renault number at the edge of the plate. So we use the equation of rho u L over mu. And then we substitute everything. So the velocity is 6, the length is 1 meter. So we take the density, so 998, because it is at 20 degrees Celsius. And you will have 5,988,000 Renault number. And it is, we assume it is fully turbulent, because it is 5 point, let's say it is equal almost 6.0 times 10 by the power of 6, and 10 by the power of 6 means 1 times 10 by the power of 6. It is transition between laminar and turbulent. And then we need to calculate the length of laminar boundary layer, whether it sufficient or not. It is it is need for us to calculate, to take it into account or not. So we calculate it by using the Renault transition here, 10 by the power of 6, and then we could calculate the value of x here, and we found it is 0.167. So it is means that it is 16.7% from the total length. So the laminar boundary layer cannot be ignored. So first we calculate the boundary layer thickness at critical, which is 10 by the power of 6. So we substitute the value. So and then we get the laminar boundary layer thickness. It is equal to 0.000835 meters. So and then because it is not given in the question, so it is okay for us to use the equation from the representative of the turbulent boundary layer. So I use the 1/7 power law. So the delta, so it is 0.000835, and then we equate with the equation, the delta equation from the 1/7 power law. So we could get the x here. So is 0.03557. 0.03557 meters. So I hope you can understand. So the purpose we calculate this one is actually to know what is the starting point of the virtual turbulent boundary layer. So this is the laminar boundary layer. So and then we have the turbulent boundary layer like this one, but actually the turbulent boundary layer is start at certain point here. So we get from above calculation, we get, so this distance is actually 0.03557 meter. So, and then we could calculate the x value, means the distance for the turbulent boundary layer only. So, mean the distance it is from here to here. So it can be calculated by using the idea of 1 minus 0.167, means the length of the laminar boundary layer, and then we add with the 0.03557 to get the total length of turbulent boundary layer, so which is 0.86857 meters. So now we calculate everything, all the data is already calculated. Then we could calculate the value of the trailing edge boundary layers. So we could use the turbulent boundary layers to get the boundary layer thickness at the trailing edge. So this is the equation for the turbulent boundary layer. However, the Renault here must be Renault for the turbulent boundary layers only. You cannot substitute with 1 meter length, because 1 meter flat plate consists of laminar and turbulent boundary layer. So you could imagine that we have a plate here, we have laminar, and so we have the imaginary, and then we have turbulent. So now to calculate the thickness of here, the delta here need to be calculated using the turbulent properties only. So that's why we take x here is 0.86875, and then we get it is around 0.01466 meter. And then we could calculate the trailing edge wall shear stress here by using the same equation. We substitute the same Renault number by using this idea. So we get it is around 47.1 Pascal. So the tau here will represent shear stress at this point, at this single point. So the shear stress that occur at this location is 47.11 Pascal. It not represent the total shear stress from here to here. So it is just to represent the shear stress at one specific point. So, and then we need to calculate the drag force. So the drag force in our previous lesson, where I show you a table where we need to use equation like this one, but it is depend to the Renault critical. So we have a 3 or 5 or 6 times 10 by the power of 5. However, in our calculation here, we take 10 by the power of 6 as our Renault critical. So the idea is we could use this equation, but we need to change the coefficient of this one, because this coefficient is showing the effect of laminar boundary layer at the beginning of the boundary layer formation. So how to do this? So you could make a very simple interpolation. So for example, if we plot all the three data, so we have it's quite connected in like this line. So if you use Excel, so you could get these terms. So you have the y equal to e exponent by the power of 0.9 x squared plus 0.0016x plus 400. So if you substitute the value of x here is the Renault number. So you substitute Renault number as 10 by the power of 6, 1 million Renault number. So you will get the value of y here. So the value of y is actually, it is around 400 here. I'm sorry, 4,000. So we could calculate the CD here by using this equation. So, and then we substitute everything. And again, so for drag force here, so we are calculating the total drag force that occur on this plate. So you need to take care about lamina and also the turbulence. So that's why we use the Renault number here is the total Renault number from here to here. So which is 5,988,000 Renault number. So we could get the CD is around 0.002552. So we substitute into this equation. So I think you already know this equation. It is quite general. You have CD 1/2 rho AU square. We substitute everything and you could get that the drag force here is around 37.51 newtons. Okay, so we go for this question. For example, we still evaluate the same plate. For example, the water is at 20 degrees Celsius, 1 atm, flows at 6 meters per second, past a rough flat plate with average roughness of 0.1 millimeters. So 1 meter long and 60 meter wide. Take the Renault transition is same with the previous question, which is 10 by the power of 6. So the difference here is, in previous question, we use a smooth plate, but now it's not smooth, so it is rough. Okay, it is rough, and the roughness is actually given with a 0.1 millimeter here. So for a unit for the roughness, so the unit is length actually, because if you're familiar with the surface roughness tester, so it will give you the value, the average value of roughness will be right as RA. So it will give you in micron. So micron means the length. So but now it gives you in 0.1 millimeter. So it is equal to 100 micron. So 1 mm is equal to 1,000 micron. So it's quite rough. So and then we calculate the same thing. So we could compare with the previous tutorial. So we need to calculate the trailing edge boundary layer thickness, and then we could calculate the wall shear stress and also the drag force of one side of the plate. Okay, so please refer to our textbook, chapter 6, 6.4, turbulent flow past a rough plate. So because the complete equation is actually there. So for example, first we need to calculate the Renault number at the trailing edge. So we use the common Renault number, rho VL over mu, and we get it is 5,988,000. So and then from the question, it gives us the roughness height, which is the, in terms of K, it's equal to 0.0001 meter. And then this is the hard part of this calculation. We need to make an estimation what is the value of lambda. So it is based on these three equations. So this equation and also this equation and also this equation. So but here this is the kinematic viscosity. Okay, but what you need to do is you substitute the value of this one, 5,900,000 into this term, and then we substitute the value of Z here with this term. So we have Z here, power of Z This is Z, Z, and this is also Z. So we substitute with K lambda, and then the K here is the constant for the von Karman. So it is equal 0.41. Okay, so and then we substitute the value of K plus here. So K plus is K times V star here. And V star is actually can be calculated by using this equation. Okay, so from here, maybe I missed on my notes there. So from here, we know that lambda is equal U, capital U over V star. So, and V star is equal to U over lambda. You substitute the value of V star equal U lambda here in these terms. So it means that you have a lambda in K here. You substitute in K plus here. So, and then you will get the value of lambda. So I skip this one. So, so all of this equation is actually the curve fitting from the previous researcher. So I hope you could read the textbooks, because in these topics, I would like you to use the equation only. So this is the hard part. So you need to equate this Renault number with all these terms. Okay, and then finally you could get the lambda. It is around 22.07. So and then after we know the lambda is 22.07, so we could substitute into this equation. Lambda is equal U over V star, and then U is 6 meters per second. U is free stream velocity. So and then we could get the V star here. It is around 0.272 meter per second. And then we also could calculate the value of K plus. So K plus here is the coefficient for the sand roughness. Okay, because the story is previous researcher using the grade of sandpaper to reflect the roughness of certain plate. So they try to plot all the experimental value, and then they will have the correlation, and they start to curve fitting to predict the changes. And now it proposed with a certain equation, very complex, like this one. Okay. So and then after we get the K here, so it is 27.14, and then we need to calculate the value of delta B here. Delta B is the coefficient for the grain sand, for the sandpaper actually. So we could substitute this one. So the value of K here is fixed with 0.41. So and then we could substitute everything. The K plus here is 27.14, and then you get it is 5.397. I'm sorry, this should be millimeters. It should have 5.3 meters, so it's okay. So because all the value is in meters. Okay, so this is 5.397 meters. So and then all these parameter is actually need to be calculated for this one. So for example, from equation 6.60, so we could use this idea to calculate the boundary layer. So we have U over V star here, which is equal to lambda, and then it is equal to 22.07, and it is equal to 1 over K ln delta V star over nu. So this is the kinematic viscosity. So and then we plus with B and minus delta B. So B here is the B, and delta B is actually a parameter that previous researchers used to show the changes of roughness. So B is a constant actually. The curve fitting value is 5.0, and 5.397 is actually what we get from our previous calculation. So if we calculate this one, so we could get the value of delta here is 0.03688 meters, and the boundary layer for the smooth plate From our previous tutorial, it is around 0.01466 meters. So it is found that when we roughen the thin plate, the plate, so the flow is changed actually from laminar into turbulent rapidly. So the delta is also increased from 0.14 to 0.036 meter. And then we need to calculate the trailing edge wall shear stress here. So it's very straightforward. So we could use this equation. So tau is equal rho V star square. So we substitute the rho 998 and the V star, which is 0.272 square. So we get it is around 73.84 Pascal. So we could also use the idea of this one. So lambda is equal to over CF by the power of 1 over 2. If we substitute, so we get the value of CF is 0.0041061. So then we need to calculate by using this equation. So we get it is almost same with the answer here. So which is 73.76 Pascal. So CF here is your local friction coefficient. Local coefficient of drag. Local coefficient of drag. And then sometimes we have a C with a capital D here. So this is the coefficient of drag force. Coefficient of drag. So coefficient of drag here, you could assume is the total coefficient of drag for the whole object. So the local means if we have a plate here, so the local means the CF at certain value of X. So that's why in our equation here, we don't have any value of area because the shear stress is not calculated for the whole area, but it's calculated for the one single point. So then we need to calculate the drag of one side of the plate. So from the equation 6.81, you could refer from the textbook here. So the relationship between the CD and the CF can be written as this one. So this is actually based on the experimental conduct by them. So they could say that, so it is okay for us to multiply the local drag coefficient, which is CF here, with 1.15. And then, but in certain textbook, they will, sometimes the ratio is increased by the researcher. You maybe use 1.20 and so on, depends on the experiment that you conduct. So if we use 1.15 based on the textbook that we have, so we could get the CD here is equal 0.004722, and then the drag force for one side can be calculated by using this equation. Now we use CD here, so and then we need to times 1 over 2 rho A and U. So the A here will reflect that now we are calculating the whole plate to get the value. So we get the total drag force is 15.9 Newton. So and then we also could use equation 6.84b to estimate the drag force. For example, the CD can be calculated by using this one, and L here is the total length of the plate, so we use 1 meter, and the K is the roughness value of that plate. So it is 0.0001 because it is 1 millimeter, 0.1 millimeter, I think. So, and then you will get CD is 0.004934. So we calculate by using the same equation. So we could get it is 53.18 Newton. So if we compare 53.18 with the 50.9 Newton, so we have 3 Newtons different. And if we compare with the previous answer, so it is around 27.51 Newton for the smooth plate. So it seems that our answer is quite good because the value is increased when we roughen the surface. Okay, so finally, this is maybe the last notes for our syllabus, because in surface roughness, in turbulent boundary layer, there is still a lot of things to can be researched. Okay, so for the theoretical, the idea that can be calculated on paper like this, I think it is enough for us to study for this until this level. So actually, if you read the textbook, the equation 6.84b is usually used in fully rough condition. So our plate here, if we calculate the Renault number based on the value of K, so I write as Renault number, REK, so rho UK over mu, so we substitute the value of K here. So it is around 599. So it is smaller compared with 1,200. So if the value of our Renault number K here is exceeding 1200, so our condition is actually fully rough. But in this question, our Renault number K here is less than 1200 here, so mean it is actually the intermediate condition. However, we could use the idea of this one, because turbulent is actually fluctuate very rough. So it means the difference between the minimum and the maximum is quite big. So based on the experience that I have, so I could say that it is okay for us to use the CD of this one. So, however, turbulent boundary layer is still a complex phenomenon, and no single equation could solve the problem. There is still a lot of research point of view could be developed for this field. So, if you have interest for boundary layer, so you may continue the research about boundary layer, especially in turbulent boundary layer. But because in many applications, when the speed increase and if you have the large area, so for sure, your boundary layer is actually in turbulent boundary layer, so means that you have a lot of things to be researched.